Far above, silver shapes cut through the thin stratospheric air, too high for most fighters, too distant for most guns. One of them falters. Oil streaks across polished aluminum. Its propellers still turn, but unevenly. Something inside has failed. Hours later, the aircraft rests in a field far from where it was meant to fly. Its fuselage is intact. Its wings unbroken. Not soldiers first, engineers? They circle it slowly. Crude hydraulics, exposed mechanisms. And in that moment, before a single report is written, the war feels different. The air war over Europe had become a war of altitude, endurance, and industrial will. 5 years earlier, when Germany invaded Poland in September 1939, air power had served as a tactical spearhead. The Luftwaffe dominated the skies of Western Europe through speed, coordination, and surprise. Aircraft like the Messerschmitt Bf 109 and the Heinkel He 111 embodied a doctrine designed for rapid, concentrated strikes, close air support for advancing armored divisions. But Germany had not built its air force for a long industrial war. Across the Atlantic, the United States watched the fall of France and the Battle of Britain with growing urgency. When the United States Army Air Forces expanded after 1941, it did so with a very different philosophy. American planners envisioned fleets of long-range heavy bombers striking directly at an enemy's industrial heart, day after day, relentlessly. By 1943, that vision was becoming reality. American B-17 Flying Fortress and B-24. Their targets were ball-bearing plants in Schweinfurt, aircraft factories in Regensburg, oil refineries in Ploiesti. The skies over Germany became corridors of contrails and flak bursts. Losses were staggering. On October 14, 1943, Black Thursday, 60 B-17s were shot down in a single raid. German interceptors rose in waves. Anti-aircraft batteries formed lethal belts around industrial cities. The message was clear: daylight bombing without escort was unsustainable. Then the balance shifted. The arrival of long-range escort fighters like the P-51 Mustang transformed the battlefield. Above 20,000 feet. With drop tanks extending their reach, Mustangs could accompany bombers deep into the Reich and engage German fighters over their own airfields. The Luftwaffe, already strained by fuel shortages and the demands of the Eastern Front, began to suffer irrecoverable pilot losses. By early 1944, the combined bomber offensive intensified under the Allied strategy known as Big Week. Aircraft production centers were hit repeatedly. Synthetic fuel plants became primary targets. The German war economy. Another technological threshold was being crossed: altitude. Most German interceptors operated effectively below 30,000 feet. Above that, performance dropped sharply. Engines lost power, cockpits became frigid, oxygen systems were strained. Pressurization was rare in operational fighters. American engineers were thinking differently. Even before the European bombing campaign reached its crescendo, a new aircraft had been conceived for a different theater entirely: the vast distances of the Pacific. In 1940, the U.S. Army Air Corps issued specifications for a bomber capable of striking Japan from bases thousands of miles away. It needed unprecedented range, altitude, capability, and bomb load. The result would be the B-29 Superfortress. It represented a generational leap. Designed with a pressurized crew compartment, remote-controlled gun turrets, and advanced fire control computers, it was intended to cruise at altitudes above 30,000 feet, beyond the comfortable reach of most contemporary interceptors. Its engines, the Wright R3350 duplex Cyclone, were among the most powerful radial engines ever installed on a wartime aircraft. Its fuselage was aerodynamically cleaner than previous bombers. Its systems were integrated, complex, and electrically driven in ways uncommon in 1940. When the first B-29s entered combat in mid-1944, they did so in the Pacific, launching from bases in China under Operation Matterhorn. Their early missions were plagued by engine overheating and logistical nightmares. Flying fuel over the Himalayas to sustain operations proved unsustainable. Yet the aircraft itself was revolutionary. And revolution, in wartime, travels faster than the machine that carries it. German intelligence services, technical attaches, and reconnaissance analysts followed Allied aircraft developments closely. Photographs were studied. Debris from downed bombers was catalogued. Reports from Japan, Germany's Axis partner, began to mention a new American bomber operating at extreme altitudes. Details were scarce, but certain numbers stood out: wingspan over 43 meters, maximum bomb load up to 20,000 pounds, operational ceiling beyond 31,000 feet. These figures suggested something unsettling. Germany had pursued advanced aircraft of its own, including high-altitude variants of the Junkers WWII and pressurized reconnaissance platforms. Jet propulsion had reached operational form with the Messerschmitt Me 262, yet resources were fragmented. Production was dispersed to avoid bombing. Fuel shortages limited pilot training. Aluminum and skilled labor were in constant deficit. The Reich was innovating under siege. The United States was innovating at scale. By mid-1944, as Allied forces landed in Normandy and pushed eastward, the skies over Europe were no longer contested in the way they had been in 1940. German radar networks still functioned. Flak towers still rose over cities. Fighters still climbed to intercept, but the balance of endurance had shifted. And somewhere beyond the European theater, a bomber existed that seemed built not just for this. The moment carried weight far beyond a single airframe resting in a field, because understanding what stood before them required understanding how the war had already changed. By 1944, Germany's aviation industry was fighting two wars at once. One was in the air, against Allied bombers that arrived in growing numbers each month. The other was against time. Factories that once operated in concentrated industrial zones were now scattered across forests, tunnels, and underground facilities. The systematic bombing of aircraft plants in Augsburg, Regensburg, and Wiener Neustadt forced production into improvised spaces. Transportation networks were fractured. Synthetic fuel plants were burning. The German aviation establishment, led administratively by the Reich Air Ministry, had not planned for a prolonged industrial duel with the combined output of the United States and the British Empire. Aircraft designs that had been revolutionary in 1939 were now being pushed beyond their original limits. The Focke-Wulf FW-190 and the Messerschmitt Bf-109 remained formidable fighters, but both were based on late 1930s engineering philosophies. Modifications extended their service life, improved engines. Specialized versions of the Junkers Ru-388 and the Ta-152. High-altitude fighter variant attempted to challenge bombers operating above 30,000 feet. But these were limited production responses, introduced when strategic momentum had already shifted. Jet propulsion offered hope. The Messerschmitt Me 262 was the world's first operational jet fighter. In speed, it surpassed every Allied piston-engine aircraft. In combat, when deployed effectively, it could tear through bomber formations with frightening efficiency. But speed alone could not compensate for industrial attrition. The Me 262 suffered from fragile engines with short operational lifespans. Production delays, political interference, fuel shortages, and pilot inexperience limited its overall impact. By the time significant numbers entered service in late 1944, Allied air superiority was already overwhelming. Against this backdrop, reports of the B-29 were troubling not because Germany lacked innovation, but because the American aircraft represented integration at scale. The B-29 Superfortress was not just a large bomber, it was a systems aircraft. Pressurized crew compartments allowed operations at altitudes where temperatures dropped below -40 degrees Celsius without forcing crew to wear heavy oxygen masks and electrically heated suits throughout the flight. Remote-controlled gun turrets were operated through analog computing sites that compensated for target speed, distance, and lead angle. Electrical systems replaced many hydraulic or manually operated mechanisms. Such features were not theoretical in Germany. Engineers understood them, prototypes existed. But wartime conditions had forced German industry into a reactive posture, constantly repairing, dispersing, improvising. The United States, by contrast, could dedicate enormous industrial capacity to a single project. The B-29 program cost nearly $3 billion, more than the Manhattan Project until late in the war. Multiple factories across the United States were retooled exclusively for its production. Thousands of subcontractors fed into its supply chain. German intelligence analysts could estimate output rates. By late 1944, American factories were producing B-29s at a pace Germany could not match even if unopposed. The implications were stark. If deployed in Europe in large numbers, a bomber capable of flying higher, faster, and farther than the B-17 or B-24 would stretch Germany's defensive network to breaking point. Interceptors would require improved high-altitude performance. Anti-aircraft guns would need recalibration. Radar systems would face new tracking challenges, and there was another factor: range. Germany had designed bombers primarily for operations within Europe. Even ambitious projects like the America bomber remained conceptual or limited to prototypes. The logistical infrastructure to sustain transcontinental bombing campaigns did not exist. The B-29 had been built for exactly that purpose. From remote Pacific islands, it could strike the Japanese home islands. Its radius of action reshaped strategic geography. Oceans became operational space rather than barriers. German technical observers were acutely aware that technological leadership in aviation was no longer defined solely by speed or armament. It was defined by integration of engine performance, aerodynamics, material science, and industrial replication. Meanwhile, the Luftwaffe's fuel crisis deepened. After sustained Allied attacks on synthetic fuel plants in 1944, aviation gasoline production dropped dramatically. Training hours for new pilots were slashed. Veteran air crews were irreplaceable once lost. The air war was becoming asymmetric, not in innovation but in sustainability. When fragments of unfamiliar aircraft components were recovered in Europe, German laboratories analyzed alloys and manufacturing techniques. Even rivet spacing and surface finishing were examined for clues about production methods. The realization grew gradually. The United States was not merely building aircraft. It was building an industrial ecosystem capable of overwhelming adaptation. And so, when an intact example of this new bomber, this symbol of industrial confidence, came within reach of Axis-aligned technical observers, it represented more than intelligence value. It was a glimpse into the future trajectory of the war. Because by mid-1944, Germany still possessed dangerous weapons, brilliant engineers, and moments of tactical brilliance. But it was beginning to lose something less visible: the ability to close the gap. And that gap would become painfully clear the moment trained engineers stepped fully inside the aircraft and began tracing its systems panel by panel. When German engineers examined the architecture of the B-29 superfortress, the first realization was not about size. It was about integration. The aircraft's pressurized crew compartments were not experimental novelties. They were fully operational, connected by a pressurized tunnel running above the bomb bay. At altitudes exceeding 30,000 feet, most aircraft crews relied on bulky oxygen masks and electrically heated flight suits. Frost formed on interior surfaces. Crew fatigue was constant. Inside the B-29, conditions were radically different. The flight deck and aft compartment maintained near sea-level pressure. Crew members could move more freely. Equipment reliability improved in stable atmospheric conditions. Missions could be longer, not just in range, but in sustained operational efficiency. Then there were the gun turrets. Unlike the manually operated turrets on earlier bombers, the B-29's defensive armament was remotely controlled. Gunners aimed through analog computing sights that calculated lead angle, airspeed differential, and ballistic drop. A single gunner could control multiple turrets depending on the threat vector. Germany had experimented with advanced fire control concepts. But implementing such a system at scale, under combat conditions, was another matter. Electrical systems powered much of the aircraft's internal operation. Wiring harnesses were cleanly routed, redundancies were built in. The Wright R3350 engines, though complex and initially temperamental, delivered immense horsepower, enabling both high-altitude cruising and heavy payload capacity. This was not an aircraft built for incremental improvement. It was designed from the outset to redefine the operational ceiling of strategic bombing for German observers. This was unsettling not because they lacked imagination, but because they recognized the years of uninterrupted industrial stability required to bring such a machine from blueprint to mass deployment. And stability was precisely what Germany no longer possessed. German aviation engineering in the 1930s had been driven by technical excellence and aerodynamic innovation. Designers like Willy Messerschmitt and Kurt Tank pursued lightweight construction, high power-to-weight ratios, and structural efficiency. Aircraft such as the Messerschmitt Bf 109 were masterpieces of compact engineering. They were agile, efficient, and lethal in the hands of trained pilots. But German design culture often favored optimization for performance over ease of mass production. American industry approached the problem differently. The B-29 was complex, extraordinarily so, yet its production was distributed across multiple massive facilities. Standardization allowed components to be manufactured in parallel across states. Assembly lines were organized not merely for craftsmanship, but for throughput. Where German factories increasingly relied on dispersed workshops and forced labor under bombing pressure, American plants operated under comparatively secure conditions. Materials flowed steadily. Power grids were intact, skilled labor was abundant and trained continuously. The difference was philosophical as much as logistical. German aircraft often represented the pinnacle of aerodynamic refinement for a given role. Fused advanced aerodynamics with industrial reproducibility. To engineers accustomed to redesigning components in response to material shortages, it suggested that the United States was not improvising under pressure. It was executing a long-term plan. War in the air is measured not only in speed and altitude, but in replacement rates. By late 1944, Germany struggled to replace both aircraft and trained pilots at sustainable levels. Fuel shortages reduced flight hours. Experienced crews were lost faster than they could be replaced. The United States, meanwhile, was producing aircraft in staggering numbers. Factories turned out thousands of bombers annually. Training programs operated continuously. Aviation gasoline was abundant. The B-29 program alone employed tens of thousands of workers. Entire industrial regions were reshaped to accommodate its production. When technical issues emerged, such as engine overheating, resources were allocated to solve them, not abandon the platform. This scale altered strategic calculus. Even if Germany developed a comparable aircraft, could it build hundreds? Could it fuel them? Could it protect the factories that produced them? Industrial mathematics began to outweigh tactical brilliance, and that was perhaps the most sobering realization of all. Because standing inside the B-29, tracing the smooth curvature of its pressurized bulkheads, examining its remotely operated turrets and electrically integrated systems, German engineers were not merely confronting superior hardware. They were confronting the visible output of an industrial civilization operating at full capacity. A capacity Germany could no longer match, and beyond the technical awe lay a deeper question. What did this mean for strategy, leadership, and the psychological balance of the air war itself? By 1944, German air defense strategy depended on prediction. Radar stations along the coast detected incoming bomber streams. Interceptor wings were scrambled. Flak batteries prepared calculated barrages based on altitude and speed estimates refined over years of combat. The system had evolved to counter the B-17, Flying Fortress, and the B-24 Liberator, aircraft whose performance envelopes were now well understood. German pilots knew their cruising altitudes, their formation structures, their defensive gun coverage. The arrival of the B-29 Superfortress threatened to disrupt that balance entirely, operating above 30,000 feet with improved pressurization and higher sustained speeds. The B-29 would compress reaction times. Interceptors would need greater climb rates and high-altitude engine efficiency. Flak calculations would require recalibration for thinner air and different ballistic trajectories, but the true shock lay in potential deployment. If such aircraft were transferred to the European theater in large numbers, Germany's layered defense network, already strained, could be stretched beyond its limits. Oil refineries, rail hubs, and aircraft factories deeper inside the Reich would become even more vulnerable. Strategic planning relies on manageable variables. The B-29 introduced uncertainty, and uncertainty in the calculus of war erodes confidence long before bombs fall. Within the command structure of the Luftwaffe, awareness of Allied industrial growth had been building for months. Reports of escalating bomber formations and expanding escort ranges reached Berlin regularly. Yet, leadership responses were fragmented. Competing priorities divided resources, jet development, interceptor production. Ground support on the Eastern Front, defense against the approaching Western Allies. Political interference further complicated decisions. Production goals were often unrealistic, set more by ideology than logistical feasibility. High-altitude interception projects received intermittent attention. Advanced piston engine variants were rushed into service with limited testing. The revolutionary Messerschmitt Me 262 was delayed in part by strategic debates over its role, fighter or fighter-bomber. In this environment, the examination of an aircraft like the B-29 was not merely technical, it was political. Acknowledging the scale of the technological gap implied acknowledging industrial inferiority. It meant recognizing that no incremental improvement, no emergency measure, could fully close the distance in available time. Some leaders argued that radical innovation could still reverse the tide. Others understood that innovation without fuel, trained pilots, and protected factories was a diminishing asset. The B-29 became symbolic of that dilemma. It embodied a form of strategic patience and economic depth that Germany, under relentless bombing and resource depletion, no longer possessed. Warfare is fought with machines, but it is endured by people. By mid-1944, many German engineers and officers were professionals first, ideologues second. They understood metallurgy, aerodynamics, engine tolerances. They knew what it meant to push machinery to its limits. Standing inside the B-29, examining its pressurized compartments and integrated systems. Some would have recognized something deeply unsettling. This was not desperation engineering. It was confident engineering. The rivet lines were clean, the system's layout logical. Redundancies suggested time for refinement rather than rushed adaptation. Even its complexity spoke of abundant testing and iterative development. In contrast, German factories were improvising around material shortages, substituting alloys, simplifying components to conserve labor, relocating assembly lines into tunnels and caves to escape Allied bombing. The psychological effect of confronting such disparity cannot be measured precisely in documents or production statistics, but it echoes in private correspondence and post-war reflections. The war had begun with speed and surprise. It was ending with scale and sustainability. The realization did not arrive in a single dramatic announcement. It settled slowly, in technical assessments, in production reports, in the diminishing fuel reserves of airfields, and in the silent interior of an American bomber that seemed to belong to a future Germany could see, but no longer reach. From that quiet understanding, events would move toward a decisive turning point, not only in the air war, but in the broader trajectory of the conflict itself. The aircraft did not reveal its full meaning at a glance. It revealed it in layers. German technical teams approached the evaluation methodically. Panels were opened. Wiring diagrams were traced. Hydraulic lines were examined for pressure tolerances. Engine mounts were inspected for vibration dampening systems. The first surprise was structural. The fuselage of the B-29 Superfortress was not simply larger than previous American bombers. It was engineered for sustained high-altitude stress. The pressurized compartments were reinforced with circular cross-sections to better withstand differential pressure loads. Bulkheads were carefully sealed, but rarely at this operational scale. In most Luftwaffe bombers, crews operated in unpressurized cabins. At extreme altitude, oxygen systems were essential, and frostbite was common. Mechanical reliability declined sharply in sub-zero conditions. Electrical systems could become brittle. Lubricants thickened. The B-29 reduced those variables. The engineering implications were immediate: extended mission endurance, improved crew efficiency, reduced fatigue over long-range operations, higher average sortie effectiveness. Then came the fire control system. Each remotely operated turret was linked to a central analog computer that adjusted aiming based on relative motion. German aircraft gunners were highly trained, but their turrets were largely manual or hydraulically assisted. Accuracy depended heavily on individual skill under stress. The American system distributed that burden across mechanical calculation. A single gunner could assume control of multiple turrets depending on attack direction. The concept was not science fiction. It was operational engineering. The Wright R3350 engines drew particular scrutiny. Delivering over 2,000 horsepower each, they enabled cruising speeds that compressed interception windows. German engineers understood engine performance intimately. Their own developments in high-output piston engines were formidable. But sustaining such power at high altitude required advanced supercharging systems and careful thermal management. The Americans had accepted the cost of complexity. They had invested in solving its problems. Production tolerances told another story. Rivet alignment, panel fit, and standardized component interfaces suggested repeatable manufacturing precision. Even under field conditions, parts could be replaced without extensive reworking. This was not craftsmanship dependent on individual factory variation. It was industrial replication. And replication is what wins long wars. By mid-1944, Germany's aviation industry had been forced underground, literally. The dispersal of production to avoid bombing introduced variability. Skilled workers were scarce. Transportation delays slowed assembly. Substitute materials altered performance characteristics. Even if a comparable aircraft could be designed, building it consistently in volume was another question entirely. Reports compiled from technical examination began to converge on a difficult conclusion. The B-29 was not simply an advanced bomber. The strategic air war over Europe intensified. On June 6, 1944, Allied forces landed in Normandy. The air superiority that had once been contested was now decisive. The United States Army Air Forces and the Royal Air Force operated with increasing freedom over occupied territory. Rail lines were systematically targeted, bridges collapsed. Reinforcements struggled to move. German interceptor units still rose to meet bomber streams. Pilots flying the Focke-Wulf FW-190 and Messerschmitt Bf-109 inflicted damage where they could. The revolutionary Messerschmitt Me-262 began to appear in limited numbers, capable of outpacing any Allied escort, but fuel shortages limited flight hours. Training programs were truncated. Replacement pilots entered combat with a fraction of the experience their predecessors had possessed in 1940. The turning point was not a single dogfight or bombing raid. It was cumulative. The examination of the B-29 underscored that cumulative shift. Engineers understood that Germany could still produce dangerous machines. But the question had become whether those machines could alter the strategic trajectory already set in motion. The American bomber symbolized depth, economic depth, industrial depth, logistical depth. And depth absorbs shock. As technical officers finalized their assessments, the realization hardened. Even if Germany fielded faster fighters, even if localized victories occurred, the broader arc of industrial capacity favored the Allies. War, at its most unforgiving level, is arithmetic. Aircraft produced versus aircraft lost. Inside the silent hull of the B-29, that arithmetic was no longer abstract. It was tangible. And outside, in the skies of Europe, events were accelerating toward a decisive phase that would test whether innovation alone could resist overwhelming production. By late 1944, the air war over Germany had entered a new phase. It was no longer a contest of reach. It was a contest of endurance, and endurance had become uneven. In September 1944, waves of Allied bombers struck synthetic fuel plants with relentless precision. Facilities at Luna, Merseburg, and other industrial hubs were hit repeatedly. Production of aviation gasoline plummeted. Training flights were curtailed. Interceptor units were grounded for lack of fuel even when aircraft remained intact. The Luftwaffe still possessed teeth. The Messerschmitt Me-262 entered combat in growing numbers. Its speed, over 800 kilometers per hour, allowed it to slash through bomber formations before escorts could respond. In concentrated attacks, it inflicted serious losses. But jets required high-grade fuel. Their engines demanded meticulous maintenance. Airfields were bombed as soon as reconnaissance identified them. Replacement pilots received minimal flight hours before entering combat against seasoned Allied crews. Meanwhile, the American industrial machine accelerated. The United States Army Air Forces expanded operational capacity month by month. Long-range escorts ensured bombers could reach targets deep within the Reich with increasing survivability. Radar bombing improved accuracy through cloud cover. Tactical air power disrupted ground reinforcements in both the Western and Eastern theaters. Even though the B-29 Superfortress remained primarily committed to the Pacific theater, its existence carried strategic implications that extended beyond geography. It proved something fundamental: the United States could design, test, produce, and deploy an aircraft of unprecedented complexity while simultaneously sustaining massive operations in Europe. That was the decisive shift. Germany, by contrast, was forced into reactive innovation. Projects were rushed. Wonder weapons were proposed with diminishing feasibility. Production facilities were bombed faster than they could be relocated. Skilled labor shortages worsened as the front lines closed in. The strategic bombing campaign intensified into 1945. Cities such as Dresden, Hamburg, and Cologne endured devastating raids. Rail systems fractured. Communications networks faltered. The coordination that once allowed Germany to shift resources rapidly across fronts eroded under constant aerial pressure. Air superiority became air dominance. Allied aircraft operated not only at altitude but at low levels, strafing supply convoys, disabling locomotives, isolating battlefield units. The sky itself became an extension of Allied logistics. Inside Germany's command structure, there was no single dramatic admission of defeat in the air. There was instead a steady recognition that each new defensive measure bought less time than the one before. The examination of advanced Allied aircraft like the B-29 had foreshadowed this realization. Even if Germany achieved localized technical brilliance, a faster jet, a heavier cannon, it could not restore the industrial depth required to regain sustained initiative. On the Eastern Front, Soviet forces advanced relentlessly westward. On the Western Front, Allied armies crossed the Rhine in March 1945. Air power supported every movement, isolating German divisions and severing retreat routes. The Luftwaffe's operational sorties declined sharply. Many aircraft remained grounded due to fuel scarcity. Veteran pilots were gone. Training standards were shadows of their former rigor. The moment of irreversibility in warfare rarely announces itself. It accumulates quietly. By early 1945, Germany no longer controlled its own airspace in any meaningful way. Radar networks were degraded. Interceptor response times slowed. Airfields were craters and debris. The arithmetic that had once been debated in technical reports now manifested in daily reality. Aircraft production could not outpace destruction. Fuel could not outpace consumption. Innovation could not outpace attrition. The B-29 had symbolized a future built on industrial certainty. Germany faced a present defined by industrial exhaustion. When Berlin fell in May 1945, the war in Europe ended not with a single aerial duel or technological breakthrough, but with the cumulative weight of sustained superiority in production, logistics, and air dominance. The climax of the air war was not merely about machines. It was about momentum, and the moment when momentum became impossible to reverse. From that decisive imbalance flowed the final consequences of a conflict that had begun with daring speed and ended under relentless skies. When the war in Europe ended in May 1945, Germany's defeat had many causes: military overextension, strategic miscalculation, the grinding advance of Allied armies from east and west. But above all, it had been a war fought under constant pressure from the air. By early 1945, Allied bombing had reduced large portions of Germany's industrial infrastructure to rubble. Synthetic fuel production, once the lifeline of the Luftwaffe and armored divisions, had fallen to a fraction of its 1943 output. Aircraft factories that had been relocated underground struggled with ventilation problems, supply shortages, and transportation delays. Rail yards were craters of twisted steel. The ability to coordinate national defense eroded day by day. The strategic bombing campaign, carried out primarily by the United States, Army Air Forces, and Britain's Royal Air Force, had evolved from experimental doctrine into sustained operational dominance. By 1944, Allied bombers operated in such numbers that losses, while still costly, no longer threatened the viability of the campaign. German interceptor forces, including advanced aircraft like the Messerschmitt Me 262, achieved moments of tactical success. But these victories were isolated within a broader strategic imbalance. Fuel shortages meant many jets sat grounded. Spare parts were scarce, pilots were undertrained. The Luftwaffe that had once stunned Europe in 1939 no longer existed in meaningful strength. Meanwhile, the implications of aircraft such as the B-29 Superfortress extended beyond their immediate theater of operations. Though deployed primarily against Japan, the B-29 demonstrated that air power could project force across oceans with sustained precision and overwhelming payload capacity. It was proof that geography could be neutralized by industrial reach. In Europe, Allied heavy bombers, B-17s and B-24s, had already dismantled Germany's ability to wage prolonged war. The existence of an even more advanced bomber underscored how far the technological curve had shifted. By April 1945, German fuel reserves were nearly exhausted. Training programs had collapsed. Airfields were captured or destroyed. The remaining operational aircraft were too few to alter the ground war unfolding across the Reich. Civilian infrastructure suffered catastrophic damage. Urban centers lay in ruins. Millions were displaced. The psychological toll of constant bombing, air raid sirens, nights in shelters, uncertainty of survival, reshaped the civilian experience of modern warfare. The lesson was stark. Air superiority was not merely a tactical advantage. It was a strategic condition that could determine the pace and outcome of entire campaigns. When Germany surrendered on May 8, 1945, the war in Europe concluded under skies no longer contested. Allied aircraft flew unopposed over cities that had once bristled with anti-aircraft fire, and as the smoke cleared, attention turned to what these machines, both German and Allied, would mean in the world that followed. Because the story of captured aircraft and examined technologies did not end with surrender. It began a new chapter. When Germany surrendered in May 1945, the war in Europe ended, but the race for technology accelerated. Allied powers moved quickly to secure German scientific expertise, research archives, and experimental aircraft before they could fall into rival hands. Among the most significant efforts was Operation Paperclip, through which the United States transferred hundreds of German engineers and scientists to American soil. Many had worked on advanced jet propulsion, rocketry, and high-altitude aerodynamics. The logic was simple. The next war, if it came, would be decided not only by soldiers, but by engineers. The Soviet Union pursued its own parallel efforts, dismantling factories and relocating entire research teams eastward. German expertise in jet engines and aerodynamics would feed directly into early Cold War aviation programs. At the same time, the legacy of the B-29 Superfortress expanded dramatically. In the Pacific theater, the B-29 had already demonstrated its extraordinary range and payload capacity. From island bases in the Marianas, it struck the Japanese home islands with unprecedented reach. On August 6 and August 9, 1945, specially modified B-29 aircraft delivered atomic weapons over Hiroshima and Nagasaki, events that fundamentally altered the nature of warfare. The aircraft was no longer just a strategic bomber. It became the platform that ushered in the nuclear age. The Soviet Union understood the implications immediately. In 1944, several B-29s conducting missions against Japan had made emergency landings in Soviet territory after sustaining damage. Under international neutrality agreements with Japan, Moscow interned their crews, but retained the aircraft. Soviet engineers were ordered to reverse engineer the bomber in meticulous detail. The result was the Tupolev Tu-4, an almost exact replica of the American design, down to cockpit panel dimensions and systems layouts. It entered service in 1949, providing the Soviet Union with its first true long-range strategic bomber. What German engineers had once studied with uneasy fascination, Soviet engineers now replicated under state directive. The technological shock that had reverberated quietly through Axis technical circles during the war now echoed globally. Strategic air power had proven decisive not simply because of destructive capability, but because of sustained industrial backing. Nations emerging from the ruins of World War II reorganized their military doctrines around that realization. The United States invested further in long-range bombers, leading to aircraft like the B-36 and later the B-52, The Soviet Union accelerated its own bomber and missile programs. Jet propulsion matured, radar evolved. Nuclear deterrence replaced conventional strategic bombing as the dominant psychological framework. The aircraft that had once seemed almost futuristic inside a quiet field in 1944 became a bridge between eras. For Germany, the aftermath was more complex. Its aviation industry lay shattered. Many of its leading engineers were dispersed across Allied nations. Restrictions initially limited aircraft development entirely, yet the technical culture survived. In later decades, German aerospace would re-emerge within multinational frameworks, contributing to European aviation under entirely different political realities. But in 1945, standing amid ruins, the lesson was unmistakable. Innovation without industrial resilience could not secure victory. Technological brilliance without sustainable production could not alter momentum. The silent study of a downed bomber had foreshadowed a global transformation, one in which air power, nuclear capability, and industrial scale would define geopolitical balance for the next half-century. And from that transformation, a final reflection emerges, not only about machines, but about what they reveal regarding power, ambition, and the limits of war itself. Standing once more inside the quiet, metallic shell of a captured bomber, one is struck by more than technical brilliance. It is the sense of scale, of deliberate orchestration, a machine born not only of design, but of industry, labor, and time. Every rivet, every pressurized panel, every carefully routed wire speaks of a civilization capable of sustaining extraordinary effort under pressure. War often celebrates tactics, bravery, and audacity. But the story of the B-29 superfortress reminds us that endurance, production, and foresight matter even more. Germany's finest engineers could marvel at its complexity, but they could not reproduce it. The gap was no longer technical. It was industrial, logistical, psychological. In this sense, the bomber became a symbol, not of destruction alone, but of a new paradigm in modern warfare, where victory is measured not only in bombs dropped, but in the depth of a nation's capacity to innovate, produce, and sustain. Its legacy shaped the post-war world, informing the Cold War arms race, strategic bomber programs, and the psychological calculus of deterrence. Yet, amid the cold metrics of production and speed, there is a human element. The engineers who studied it, the crews who flew it, the civilians who endured its consequences, all remind us that war is lived, felt, and remembered through human experience. The moment inside that aircraft, silent, precise, almost impossibly advanced, remains haunting. It is a meditation on ambition, ingenuity, and the sobering reality that technological superiority alone, when combined with scale, can alter the course of history. In the end, the B-29 was more than a machine. It was a revelation, a glimpse of the future, and a mirror reflecting the limits of human endeavor in the crucible of war.